Hi everyone, this video is for the second problem. When approaching classical experiment problems, the first thing you'll want to do is identify what experiment or experiments you're using. So here you see that it is using the Rutherford experiment. So let's just diagram out the Rutherford experiment to remind you what is going on. So here you have a metal sheet and you have a particle, and then the particle is sent through the metal sheet. And then there are two things that normally happen. The first is that all the particles go through the metal sheet, some changing direction only slightly. The other is that most particles will pass through, but you will see some particles deflected back from the metal sheet, scattering back on the side from which they were sent. So let's take a closer look at what could be going on in the experiment if a particle hits a metal nucleus on the way through. So let's say your particle is lighter than the metal nucleus. If it hits the metal nucleus, if something light hits something heavy, the lighter object will bounce off the heavier one and go to the side. Think about a ping pong ball hitting a bowling ball. If the ping pong ball hits the bowling ball, the ping pong ball would just bounce off of it. But if it's a heavy particle, the heavier particle will only slightly be affected by the metal nucleus. So if the metal nucleus is lighter than the particle, you're just going to see slight deflection from the particle. Think about a bowling ball now hitting a ping pong ball. The bowling ball will only change path slightly after hitting the ping pong ball. So now we see they give us some information about the metals. So let's write the metals in order from lightest to heaviest with their masses under them. So now that we have that written down, let's take a look at what the problem says. For the aluminum, titanium, and manganese, there is almost no backscattering observed. So if there's no backscattering, we see from the diagram that that indicates that the particle is heavier than the metal nucleus. So that means that the Wuhan mass will be greater than the mass of the heaviest nucleus in this group, which is manganese, 55 AMU. So for the next three metals, which are gold, tin, and iron, we see that there's backscattering observed. So that indicates that the particle is either lighter or the same mass as the metal nucleus. So therefore we know that the mass of the Wuhan is less than or equal to the smallest mass of that group of atoms, which is iron, 56 AMU. So that means we know that the Wuhan mass is less than or equal to 56. So if we know from the first set of metals that it is greater than 55, and we know from the second set of metals that it is less than or equal to 56, that means that we can say that the mass of the Wuhan is approximately 56 AMU. So now that we have that, we'll want to start on the proportionality aspect of the problem. So we're going to follow the same steps that we did in our earlier proportionality videos. The first thing to do is identify the two particles that you're dealing with. So here we have the Wuhan and the alpha particle. Next, we want to determine what variables we're working with. So we see we have deflection, speed, and magnetic field. Then we also see that they tell us that this is the Thomson-Aston experiment. So when those variables and the Thomson-Aston experiment appear, you should think about the expression deflection is proportional to charge times velocity times magnetic field times 1 over mass. So you'll want to write that expression, and then remember, since that we have 1 over mass, you'll want to put a semicolon and then an m next to it in order to make the factors easier for us to work with. So next we'll want to write in the two variables we're comparing. Looking at the problem, we are looking for information about the Wuhan, and we have information about the alpha particle. So you're going to want to put the alpha particle on the top box, and then the Wuhan in the middle box. And then the bottom box will always be the factor line in proportionality problems. So now it's time to start filling in information that they give you. So we see that it says that the Wuhan travels at the same speed as the alpha particles. So that means the factor for speed will be 1. Next, we see that it says the magnetic field is 60% weaker for the Wuhan. So you might be tempted to say that it should be 60% as the factor. But 60% weaker means that if you take the alpha particle magnetic field strength, it's going to be 60% less than that. So you're going to want to take 100%, which is what the alpha particle magnetic field is, and subtract 60% from that. So it's actually going to be 40%. So if it's 40%, that means that to get from the alpha particle to the muon, you're actually going to multiply by 4/10. So then lastly, we see that the observed deflection is 6% of that of the alpha particle. So 6% of the alpha particle, that just means you have to multiply by 6%. So the factor in this case will be 6/100. So notice that these 2% are difficult to put into the factor line. So when dealing with percents, you want to make sure that you're taking the time to read what the problem is asking and understand how the percent is being used. In these cases, the 2% are used differently. Now, turning to the mass, we know that an alpha particle is 2 protons and 2 neutrons because it's just the nucleus of a helium atom. That means that the mass is going to be 4 AMU because a proton and a neutron both have a mass of 1 AMU. For charge, the neutrons don't have any charge, and then there are 2 protons, which both have a charge of 1.6 times 10 to the negative 19 coulombs. So that means the overall charge will be 3.2 times 10 to the negative 19 coulombs. So next you'll want to put that charge information into the table, and then also the mass information. Then from our discussion earlier about Rutherford, remember that we determined that the muon mass is approximately 56 AMU. So you can write in that information as well. Now it's time to calculate the factors. So remembering that the top times the factor equals the bottom, the factor for the mass is going to be 14. Then since the expression uses 1 over mass, that factor will be the inverse, so 1 over 14. So now we have all the factors written in except for charge. So when we solve for what's in the box, we get 21/10. Now to find the charge of the muon, we'll have to multiply the charge of the alpha particle by the charge factor, 21/10. So when we do that, we get approximately 6.72 times 10 to the negative 19 coulombs. So that's the final answer. Thank you for watching. Hope this video was helpful.